do whatever you like, to be honest.
Might as well use mine since it's sitting on there.
Okay, all right. If I get you to go, you're going to go first time, yes. So.
Sorry, I didn't want to. It doesn't have to be done now.
No, we'll get set up now.
Yeah. Really need the screen. Volts, that's going to be volts over there. That's easy enough then. Are you going to do it? Okay, thank you. Oh, you've got it round the wrong leg.
Do you want to try the pointy thing, or are you just going to use your mouse?
I'll just use the mouse.
Okay. So,
you want me standing on this side, don't you?
yes, please.
Yeah. So
the orange zone 1 in it.
Yeah, it's just it's got a little double. So.
So just 11:05. CT scan. So that's not on it. Yes. That's an RX01. The RK05.
Isn't it just so much nicer now we will have HDMI everywhere?
Although, having said that, as you can imagine, people come to this.
So
They've
this
still got
Oh, really?
Yes.
Yeah, well, of course, with a thing like this, that's
Yeah, that's brilliant.
And if you know anyone who needs
one in the bottom remote there.
Oh, sorry. I was wondering where that voice was coming at me from. What's that?
It takes composite or RGB of many sorts and produces HDMI out.
Oh, right, okay. Oh, that's cool.
At least one of each of these.
Okay, we're all set. That was easy. You don't need to listen to this. You've heard this before. Yep, just as long as you don't snore. Actually, you may not have heard before because this spends a bit more time talking about DecLegacy. You'll have heard quite a bit of it before.
Do you still look at, I mean, who looks after the ATC stuff at TNMRC these days?
You know what? I don't know. Is a simple answer.
That's fine.
It was.
That's an excellent answer.
Yeah. Well.
Are you more inland?
Pete's. Yeah, that Pete. He looks after it anyway, boy. So he knows how it works. But I don't think anybody does talks on it or anything like that. It's a bit of a shame. I need to get down there again, to be honest. I can't get out with it
how the pubs are coping with it, are they going to open? And now, it's, there are issues, not issues, there's quite a bit of work because people can't get staff, opening times are changing, those other services they're offering are changing. There's still a lot offering minimum meal times or not offering meals at all.
Yeah, we've got that problem around where I am. Yeah. They've all survived, which is a good thing. My actual local but it will reopen suppose shortly. But he nearly went bankrupt.
I mean, one of our pubs next to us, it's been a revolving, well, we've had 2 or 3 that have been revolving doors, and this one particular one, I can't think who bought what, but basically it was a kind of a victim of a takeover in that there were 2 pubs next to each other, which ended up being run by the same pub co, and they were told they had to sell one of them.
Okay. By the pub code.
No, by the Monopolies Commission.
Oh really? Oh okay.
They were allowed to go ahead with the takeover as long as they sold where they were too close to each.
You don't tend to think of that sort of thing happening at that sort of level, do you?
Yeah, but no. So there was 2 others. And one of them went to this new pub co called Red Cat, and they're totally incapable. It's not. It doesn't. I don't know why they bought it because it doesn't fit with their portfolio. So the guy who was in fell out with them because he just couldn't get anything done. Eventually gave them his lease back. They then said, oh, we've got somebody who will come in and do it. So for a while it was run by the staff that used to be the staff, just looking after it. And somebody from the pub co popping in every now and again. The person who they recruited to run it didn't check it out or anything. I don't know what he'd done. But he walked in, looked at it, put the keys back on the bar and walked out again.
Oh, that's pretty fundamental.
And then the next guy just wandered off. So it's been, and it's now got a new tenant in, but there's been quite a few. But we've not, we've had 2. We've had one that's closed and they're trying to avoid reopening it. And the council, well actually the council never refused or accepted the plans. So they appealed on the grounds of non-determination. And the council, sorry?
Make a decision for board,
Well, the council had already, they were about to make, if they'd left it a week, the council would have said no.
Right, okay.
And
So that would be the wrong answer.
it would be the wrong answer. But the planning appeals officer virtually supported everything in the council's judgment, plus came up with a few more reasons of his own why it shouldn't be accepted. So I think they've gone away with a clear deal. So I don't know what they're going to do. So they were saying we're going to build it, we're going to build 20 care homes or something like that. And the planning officer said, well, why would you want to do that? Because you've got a surplus of care home beds in Trafford at the moment, and you don't actually need any more care home beds. You've said that these other pubs, but you haven't shown how much available capacity the other pubs have. You haven't really shown, because nowadays if you want to close a pub, convert it to something else, you have to show that it's not profitable.
Yeah.
So if you haven't shown it's not profitable, you've shown that you advertised it in the middle of COVID, but you didn't really advertise it, you stuck it on obscure websites, you didn't make absolutely no attempt to market it.
Work, isn't it?
Sandwiches. If you've ordered a sandwich, it's ready.
Sorry, did you say sandwiches ready?
Yeah.
Yeah, Yes, it's interesting because we went through all of this when the landlord, absolutely excellent landlord, really, ran an absolutely super farm between him and his wife. They did excellent food and so on. Apart from COVID, knocked him out badly, but he did manage to survive COVID. But he just got fed up with the pub business. He was in it for 15 years, and he'd done enough of it, and they've gone on to do something totally different. But the owner of the property looked into what to do with it. Well, of course, the first thing is you've got to sort of say, that's our pub. Don't mess with it, basically. But when he looked into it, the best use for it was for him as a pub. But he had to do quite a bit of work on it. They've gone through and they've completely redone all the electrics. They've re-engineered the room. So, you know, and it's taken.
We had one shut for a while because, I mean, a picture was, and it's not doing well now for various reasons. But it's a listed building, and they've converted it into an Irish pub, and charging ludicrous price.
Yeah. Well, I hope they don't do that with my house.
When you've had your lunch, I want to ask you just a little something about the 1124. Just a little tiny thing. Are you talking about the Lake District itself or something at some point? Maybe tomorrow, I think. I want to miss that. Is it like just that, the hills and stuff?
Just a compression of my photos from.
Oh, right, yeah. Oh, your radio.
Yeah, it's not radio, it's just sort of pictures to
Oh, okay.
Camille, for example.
Yeah.
But no idea about surrounding it. So.
I know North Wales better than I know the Lakes, really.
I've not ventured out at all. We did Gough and I've done the Isle of Bute, which is not really
You're supposed to get Sahara.
We got really lucky. We went for 3 days, and there was one day where it was good enough to, which I found out subsequently is quite rare.
Is that right?
Yeah, people go for a week and then leave.
So, Mark, do you go to the Barrow pub regularly? Or is that
Yeah, when we come.
Because there isn't one here, is there?
No. No, it's Barrow or Morecambe. Yeah, it was at AGM last week, so I went for that. And actually it was a good turnout, which is always encouraging because people tend to be taking a step back when.
Well, they seem to want me back again, so I'm not quite sure what they're going to want me to talk PCB talk went down well.
Yeah, yeah, no, it was a really good job. It was really good.
We just had the 80th convention, of course, last month. And it was the first time in many, 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 many years that I wasn't giving a talk at that. Most times I end up by doing a talk on something.
It's RSGB.
RSGB,
Yeah.
Milton Keynes.
Yeah, I'll go next. I'll go next year. I'll try.
You should go.
I'm sure it's good.
It's a good event. And a good social contingent go to it.
Yeah.
And, all the people who work on the air will be there. So it's a really good sort of reunion, particularly this year, after 2 years with COVID stopping it. Find people getting together. And to begin with, almost, forgotten how to do the socialising bit. And then, I remember how we used to do this. Isn't it nice? Nice to be able to socialise again.
Yeah, I was saying it's only. It's not a novelty anymore, but it was a novelty for quite a while.
It was, yeah.
To actually socialise, yeah.
Well, before that, we had the GMDX convention in April, when of course this is up in Scotland, in Stirling, and Lee Cranky was still trying to be different, and she was still nominally insisting on face masks everywhere. Anyway, so I wasn't very happy with this, but we pitched up the hotel, this is in Stirling, and there wasn't a face mask to be seen. None of the staff were wearing face masks, none of the punters were. Everybody was just wandering around and socialising. Well, look, isn't this great? But we better not tell Sturgeon. I think nobody seemed to be telling him. Everybody was just viewing it as being a political gesture by her, which of course is exactly what it was. Then we had the CDXC AGM down at Loughborough. Similar sort of thing, although there was no mask mandate by then, but there was still the slightly odd feeling of socialising again. And then of course we had the convention at Milton Keynes last month.
Are you following the latest Bouvet attempt?
I don't much care for their antics. They're pretty well only really operating on FT8, which I don't do. Have no interest in whatsoever. They're not endearing themselves to the DXing fraternity, let's put it that way.
Right.
With their aggressive, we'll do it our way and damn the rest of you sort of attitude. Which they seem to be taking. So, I mean, maybe towards the end, if they do a bit of CW operating, I might just poke my nose in and see if I'll work them without any problems. I've got a good enough setup to be able to do that, but they need to be there when the propagation is there. At the moment, they're not interested in doing that. At the moment, they're only really going. They say they're working the Japanese pilot down, which is fair enough. But the result is they're not on at the times when we have propagation in this country.
Oh, okay. That's interesting. Because it's costing something like $700,000 or something to get there.
Sorry, say again?
It's costing about $700,000, I think.
Oh yeah, going to these places are not cheap.
So this is radio amateurs going to unusual places to operate.
Right.
Well, do you know where Bouvet Island is?
Do I know what?
Bouvet Island.
No.
So I think it's Norwegian. The Norwegian stuff flagging it. It's off the coast of the Antarctic. And there's been several attempts recently to get ships there. And I believe I'm right in saying it's the Roaring Forties. So this tends to be terrible weather, 40 degrees latitude, south latitude. And there's been several aborted attempts. And I think they have to get a helicopter onto the island. But if you look at the number one location that people want contacts from, Bouvet Island's at the top.
Okay. No, it's not.
Is it not? Is it North Korea?
Yeah.
Oh, okay.
Depending upon what list you look at.
Right.
So all lists have North Korea at the top, without exception.
Right.
But then Bouvet for North America is I think number 3. Bouvet for Europe is number 2.
Right.
So it's well up there.
Yes.
But it's hard to get to.
Yes.
And very expensive to get to. And North motorway isn't so much hard to get to or very expensive to get to, so you might not survive the actually trying to do it.
No one's going to risk themselves for it. So in terms of bands, I did see something about SSB and CW. Are they saying 80 metres and 160 metres? Did I read that right?
No. I'm not keeping that close to tablet, but
It's very disappointing if
they're
they're
more
just
like
going to
saying
do FT8.
they'll do FT8 until there isn't any more of that. Well, that'll be never. Then they might do some single sideband. And CW, quote, if anybody wants it, with a kind of an attitude I don't like, which is, instead of providing what people want, what they're saying is what they'll produce and we have to put up with it. And that's not the right way of doing it. I mean, when I was going on major D expeditions, we would take clear soundings as to what the need was, and we'd try to address that.
Yes. Because at the end of the day, they're probably getting a huge amount of sponsorship for that money out of people who want to contact them.
For Anderson, they would have done. And they didn't get CDXC or GMDX sponsorship because of their attitude.
Oh, right, okay.
But then our sponsorship is relatively small. I mean, typically those two clubs between them, if they manage to pony up £1,000, that's all it will be. Whereas if you look at things like North California DX Club, they might spend $10,000 or even $20,000 on the expedition. I'm not quite sure whether they must have done.
John, do you have anything in your coffee?
Oh, I forgot about that. No, just milk, please.
Just milk?
Yeah, it's fine. Oh, okay, thank you.
So, do you know Burns Fisher? Burns Fisher is a long-time VMS engineer. Actually, kind of like my predecessor. I took over some of his projects
Right.
at VSI. So he retired a few years ago, and maybe he's kind of having on a retainer. So if there's a really tricky issue with something he wrote, then he can come back in for a few hours a week or so. But he's a hand. But he's now involved with AMSAT.
Okay, yeah.
And
Bloody
he's
hands,
like
aren't I?
the
You're going to have to take her out, you're going to
engineer
have to take
now
a
for
sip.
the software that goes into
Yours
the
look great.
CubeSats.
Very good.
Because they basically contacted him right after he retired, and he said, "You know something about software engineering, don't you?" And they were like, "Well, we've got these CubeSats, and it's getting harder and harder to sort of tie all the software together." And Burns took one look at what they were doing, and he said, "I see what your problem is. You need an operating system." It was just all routines that were being called at random from timers and things like that, but nothing to actually coordinate everything. So Burns sort of did a bit of research on what would be best to use, and I think they ended up with something like FreeRTOS or something.
Okay, yeah.
And then Burns ended up writing a lot of the code for it, doing a lot of the telemetry and things like that. But it's interesting because he's got this whole array of antennas in the garden now, all motorized.
Bit. Yeah.
And he's got this map with every satellite that we have up there. I think they've got something like 8 of those CubeSats now. They're launching a few larger ones next year. Well,
Okay.
hopefully, because they sort of they go along with a commercial payload.
Yeah. Yeah.
Apparently, there's some requirement on commercial carriers to set aside a little bit of their capacity for
Okay.
basically free rides for scientific experiments, and that's where those, I think, 10 by 10 by 10 centimeters.
Oh, okay,
those
that's the-
CubeSats.
right.
They're like really small
Yeah, no, they're amazing, aren't they?
satellites, but it's this whole. It's basically just a stack of printed circuit boards
Yeah.
with a little bit of an aluminum casing around it with solar panels on each side, and that's it. And then they have this. Burns showed me how they basically solved the problem because they want to send and receive data, so they need an antenna.
Can we take your plate for you?
Thanks. So what they've done is they've got this spring-loaded antenna that's being kept in place during launch by a little bit of wire. And then when it's in space, then they basically send high current through that bit of
Okay,
wire
yeah, I
to
was gonna say.
burn it away, and then
Right.
the antenna deploys.
Hopefully.
I thought it was a really smart way to do it. Well, so far they've only had one antenna failure, and that was because the wire burned, but then the antenna got stuck behind some other component that was sticking out just a bit too much.
And presumably they've got no control over it. It's got no ability to manoeuvre once it's up there. They won't have
Right.
jets or
Yeah.
anything.
No, they're the cubes that they want to launch next year have some maneuvering capability.
Right.
But they're like they're a triple cube, so it's 13 by 10 centimeters. So they basically take up 3 launch slots for a single satellite.
It is fascinating. Yeah. I've got a handheld antenna, 2 metre 77s. So you need 2 radios
Right.
to listen and work, and about 5 hands, I think, is what it boils down to. So,
Is that the SL?
working satellites. Yeah. So, but having a altitude azimuth mount for your antennas is a prerequisite if you're doing it from home
Right.
properly.
Yeah.
So, have you got one of those, John?
No, I've done a little bit of satellite donkeys years ago, and it was a new thing. But where you really need LNAs is when you're doing moon bounce.
Yeah.
And I have done a bit of that on 70 centimetres for 30 megahertz.
Right.
And that's interesting. Big sat.
Bouncing your radio waves off the moon.
Yes.
Yeah.
It's not a very good reflector. You need an awful lot of power.
You need quite a lot of uplink.
Yeah, you need a lot of uplink power because it is literally it's like primary radar, except the thing isn't made of metal. So,
Right.
but it does work, and it's fascinating. If you send a string of dots on Morse code, it takes about half a second round trip. So you go did, and so you know you've done it.
Yeah.
You know when you've done it
You know when
because
it's working.
but my God, it's difficult. It'd be a lot easier now. I mean, back then, producing 400 or 500 watts on 400 odd megs was really quite difficult. Nowadays, you can do that relatively easily with modern solid-state technology. But it's still a challenge.
What did you use then? 4CX250s?
Yeah, exactly that. Yeah. A pair of, actually.
Only
Since
two.
you ask. A
Only
pair,
two?
a pair of
You're getting towards the full esoteric end of maturity.
yes,
rather
and
than- maybe not quite, but
I mean, I was probably running a kilowatt of output from the amplifier, and I would have had something like 30-ish dB of antenna gain.
yes.
So you start doing the maths on this, you're talking about megawatts of effective radiated power.
I mean, 4CX250s were fairly easy to obtain.
Yes, they were.
But actually getting the right chimneys for
Getting-
them,
yeah.
because they're metal fin valves.
The
so-
expensive bit was the chimney.
Yeah.
Because it was
Just pick
effectively
these out.
in fact, it's only that big, the valve, but it's got fins that you force air through.
Right, yeah.
And so it sits in a chimney, which also has the anode connections and so on and so forth in it. And you force air up through it, and you have to have forced air conditioning on before you can turn the heaters on.
Yeah, when I was in university, we had a pretty active amateur radio group in the university. They had these, I think they had 5 kilowatt transmitters,
Wow.
things like that. With, and the building they were in was, I think, 30 stories high. And they had these huge antennas on
Yeah.
top of the roof.
This is the sort of thing students do.
Yeah, I mean, it was all funded by the university.
Yeah.
And I think a lot of the equipment they got was just stuff that was being chucked
Yeah.
out of the lab because it was
That
outdated.
that
and,
happens a lot.
4CX250s were, you could get second-hand ones where I lived, because at Daresbury they used to have a thing called Nina, which was synchrotron, I think, I can't remember. You know, a ring,
Right.
not linear accelerator, but and in Daresbury had two things. It was called medium energy physics.
Right.
So they had rather a large Van de Graaff generator in a 200-foot
Yes.
tower or something. And they had Nina, which was a ring accelerator, but it used quite a lot of 4CX250s. And they they used to change them rather than wait for them to pop. They would change
They change them on time.
Yeah, they'd change them on regular
Yeah,
intervals.
that's what we used to do. It's very interesting. We have, fairly close to where I live, we have an old BBC transmitter station. And they had 4CX250s as the driver to the driver to the driver of the, so about 3 steps back. And and then they said to the amateur radio world, well, we've got these, do you want any of them? So, yeah, we'll have a couple of those. And I said, so we went along, and he said, do you want anything a bit bigger? So the next one was a 4CX1000, which is about that sort of size. And the final output thing was a 4CX10,000, I think it was, which is, I think a valve a foot across, half a third of a metre across. But there comes a point at which the availability of the valve is only the beginning of your problems.
That's the tower at Daresbury.
Oh, right.
So, basically that has a belt in the side.
Let's have a look there. Oh yeah, no, okay, nice. Right, excuse me, I must do it for the loo before I start doing my...
Actually, these days, the ring was a 4 giga electron volt ring. But actually, that place now, you would be interested, because that's the home of the Hartree Centre.
Right.
And do you know what's at the Hartree Centre?
I've been to this radio station, Brunton in Sweden. It was, I think it was built in the 1920s for transatlantic transmissions, and they just, and this is all just part of one antenna system.
Yeah.
They actually use to generate the transmission frequency.
Yeah. The low frequencies you need one antenna.
Yeah. I think it was 2,000 meters or something. Brighton, in Sweden.
Okay.
Radio station that was built in the 1920s for transatlantic telephone communications. So I think it's some 2,000 meters or something. So you've got
Yes, that could well be.
huge towers.
2,000 metres, my word. Yeah, yeah, could well be.
Yeah, well, it's generated off a spinning generator.
Yeah. Yes, could well be.
Yeah, so you have this whole
Oh, yeah, there we go.
row
Yeah.
that's just part of one antenna system.
Yeah. So you can see the wires fusing together. Sturdy curtain style of thing.
Incredible.
Yeah. There's some astonishing constructions out there, some of which still exist.
Well, and just it just mind boggling if you realise that goes back years.
Yes. Well, it goes back to the very beginnings of radio communication. That's right. And it's one of the things which always impresses me is people of my age, in the 70s, we've seen an entire computer revolution.
Right.
From the very beginning.
Yeah.
Pretty well. Not quite, but almost. It's quite extraordinary. There's never been an industrial revolution quite like electronics.
Yes.
No, I mean, I always, when I'm at the museum talking about the baby, and people say to me, haven't things come on? And I said, yes, but what happened when we went, this, if you look at, we've got a picture of the computing department at one of the American universities. This was your computing department. And, you went from how many editions can you do a second? So even if you have 100 people, you've got 1,000 people in the room. They're not as fast as the slowest electronic computer. And what yes, we've come on. It's taken us 50, 60, 75 years to get there.
Right.
What that go electromechanical calculators or even electronic calculators to computing, which just an iPad was 10,000 times faster than the baby, but is the baby 10,000 times faster than it? You went to take something.
But then, I mean, look at the Witch. I mean, its mission detail was to be no quicker than people could do it with
That's right.
but it could do it 24 hours a day, which people can't.
Right.
No.
And they actually excelled at that. It was good at that. This is a relay-based system.
Oh yeah. I mean, having spent a year doing that.
Yeah, you'll know the problem, won't you?
Yeah. After about a week, the arm fell off. And after 2 weeks, I was quite quick at it. We used to have competitions in our lunch hour.
How sad is that?
Yeah. I mean, you know the definition of an actuary, don't you? Sorry?
The definition of action?
Yes.
Yeah, go on, what's your definition?
It's somebody who found accountancy too exciting.
Yes, that's the one I knew of, yes. Yes, indeed.
And when you've got your two reference volumes entitled the mortality of insured lives between 1949 and 1952, then you know you're into exciting times there.
You are possibly one a sad person. Look, there's people who think what we do and things like this is sad as well.
Yeah, they probably are.
It's one of the reasons why.
One of the things I always find interesting is that if you look at, obviously there are two things in mortality. One is obvious, that actually if you live to 22 or 23, then you're likely to live a lot longer.
Okay.
Actually, the death rate of 18 to 22-year-olds, particularly males, is quite high.
Yes.
But the other thing is that people are much better at evaluating their mortality than the statistics are. So basically you offer two sorts of contracts as an insurance company. You offer a life policy where you want people to, you're trying to choose people who live, because if they do then you get more premiums for them and you've got more money to pay out. And the other sort of policy you offer is an annuity, where you hope people will die because then you don't have to pay so much money out. And so when you offer life policies, you tend to have what's called selection, so you get them to fill in forms and you talk to their doctors and stuff. If you're doing a proper life, then these models are going to so if you're doing that, then but even though you've done all that research, you've checked, then the mortality of annuities is much lower than the mortality of people who take out life insurance policies.
Isn't that interesting? Right, we better get this show on the road, otherwise we'll stay on the night.
Yeah.
Yeah. Yes. No, I'm Marshall. Next to us, sound test and stuff before anything.
Do you want to use the microphone? I don't usually
Yeah.
do that.
Is that all right?
I can do it.
1, 2, 3, 4.
Such a small room.
Yeah. I'm streaming you as well.
Oh, are you? Oh,
Is that all right?
Okay, yeah, okay. I'm a CW.
You sure that's all right?
Yeah, it's okay. I don't know if I use the microphone, but I will.
I don't probably know to this. Right. John's going to do his talk in a couple of minutes, so if you can grab a chair. Thank you. Do you want to hold the microphone? It's probably better, isn't it? Okay. Have you got enough hands?
I would say, yeah.
Right, Nick. Just double check that I'm doing this right.
Have to stroke it nicely.
So if I just put that over here so you can grab it when you're good to go,
Yeah, sure.
then that's out of the camera.
Okay. Yeah, it's on the verge of taking off at the moment. Okay, testing 1, 2, 3. I'm not used to speaking into microphones, so bear with me a moment. Good evening, good afternoon. Can everybody hear me? That's the first thing. Well, actually, no, I don't. I do Morse code. I can do the presentation in Morse if you'd like. Okay, good afternoon, everybody. Thanks for having me along. I should, at the outset, just sort of say that my involvement with DEC computers doesn't even begin to stretch to the level of involvement you folks have had and the knowledge you've had. It's been really interesting talking with people during the course of the morning and just catching up with stuff and actually reminding myself of some of the things that I was working on. But I had a limited period, about 7 or 8 years, of working on DEC machines back in the 70s in air traffic control. So that's what I'm going to tell you about today. If I can manage to work out how to make this work. Right, so why isn't... Yeah, thank you. Yeah, I didn't really want to do that. Let's just do it this way. That's better. Okay, so sort of general presentation plan, just a general introduction, who I am, where I come from, and so on. Most people don't really have much of a clue about air traffic control, what it is, what it does. Most people think it's really a man sitting in a control tower, and that's the beginning and the end of it. That's actually a relatively small part of it. So we'll talk a bit about the function of air traffic control and how that evolved in the post-war era. It might surprise you that there wasn't really an air traffic control until the Second World War. It's something which started evolving during the Second World War and became more developed afterwards. So it's a relatively new thing. We'll talk about flight and radar data because that moves us on to how computers started getting involved in it. And in particular, we'll talk about the impact and limitations that were placed on us by the technology of the era. That'll lead us on then to early computing in ATC and particularly into the role of DEC systems. So without further ado, let's see where we get to. So me, well, I was an air traffic engineer with the Board of Trade, which eventually became the CAA, Civil Aviation Authority, but actually really National Air Traffic Services, which is the delivery part of the CAA. So CAA does regulatory stuff. National Air Traffic Services provides the resources that are needed for air traffic control. In 1973, at the tender age of 22 years old, I was sent out to the United States on a IBM mainframe course as a hardware engineer. And spent a whole year out there. But whilst I was out there, I discovered software and decided software was far more interesting. So I ended up by moving across into software. That made me an absolute guaranteed target for becoming a diagnostic programmer because I understood how the hardware worked and I was also getting okay at doing software as well. So I did that for a few years, and then radar data processing came along as a project, and I thought that could be quite interesting, and that was where DEC comes into the story. I did a lot of work on the PDP-11s, and who's ever heard of a DX-11B? Anybody? Oh, good. That's okay then. I don't remember much about it, but I'll tell you what I do remember. And then after that, after I'd done that for about 5 or 6 years, about 31 years old, I escaped into industry to do the same thing all over again with the military side of things. So I was involved with air traffic control communication systems for about 20-odd years. So let's start off talking about the function of air traffic control. What is it? Well, actually, it turns out you can describe the function of air traffic control in one simple sentence, and there it is at the top. The safe and expeditious movement of air traffic through the airspace system. Well, that's a load of gobbledygook for a start off. But if you think about what it means, first of all, we try and make air traffic safe. It's a good idea to avoid aeroplanes banging into one another. They don't really like that. And once you've done that, then you want to do it as quickly and as efficiently as possible because airplanes are pretty expensive things to run. You don't want them hanging around in the air longer than they need to. So the expeditious bit comes in after we've done the safe. And to do that, we have essentially a whole bevy of people, but there are really two major functions in there. The air traffic controllers, which is what you always hear about, they are the people who actually talk to the aircraft. They provide instructions and information during the course of the flight that they are actually currently controlling. We'll talk a bit more about that later. They manage arrivals, departures, and what's called en route phases. So it's pretty obvious, aircraft taking off and landing. Most people know about the idea of an air traffic controller in the tower managing takeoffs and landings. What most people don't think about is what happens once the aircraft has actually got away from that airfield and is now on its way to, let's say, the United States or something like that. That's what we call the en route phase of flight. And of course, you can't look out the window to do that. You have to use radar. And part of that is ensuring the safe separation between aircraft. There's various ways of doing that, but one of the obvious ways is to provide instructions to the aircraft so they don't go banging into one another. There are other ways, but again, they're all part of the air traffic control function. If things do go wrong, then coordinating emergency responses is also quite important. Yes?
What do they classify as safe separation?
Well, there's a good question. If we get into that, we could spend all of the presentation talking about that alone. But essentially what we do is if you've got two aircraft who are converging on one another, they must be a minimum of 1,000 feet vertically separated. Okay? And if you've got aircraft which are tangentially crossing one another, even if they will not cross and meet in the middle, then it will be 500 feet. And that's part of a circular rule which keeps on going up. So if you've got an aircraft, say, at 20,000 feet, the aircraft going in the opposite direction will be at 21,000 feet, then the next one going in the original direction will be at 22,000 feet, and so on all the way up until you get to space. So that's a simple answer to what is actually a very complicated question. There's other rules as well. There's horizontal rules as well, horizontal separation rules, but the vertical one is a principal one that is used for separation purposes. And if stuff does start going on, this doesn't need to be an emergency. Well, it doesn't need to be an emergency which is life-threatening. It could simply be that an aircraft has a rough-running engine, or it has somebody's not well on board, or something like that. All of that is coordinated through air traffic control. So they have an important function there. Sitting behind here, this is the people you never hear about, the air traffic engineers, who basically design, implement, and manage and keep running all of the technology that is needed to do all of this stuff. There are nearly, well, in fact, there are as many, probably slightly more these days, air traffic engineers as there are air traffic controllers. They're the hidden people that you never hear about, the techie geeks. That's what I used to be. Let's just talk for a moment about civil versus military. The side that I was involved with was principally civil, but as you can fairly easily work out, we're all flying in the same airspace. It's the same lump of air. So we need to have a way of coordinating stuff with the military. And what this actually means is that we end up by doing a lot of joint projects together, civil and military projects together, because of us operating the same airspace. There's a lot of cooperation between the two. Most of the projects that I worked on had some involvement with the military side of things as well. And that, to a certain extent, limits, first of all, the amount of information which is out there in the wild. If you go researching air traffic control development at London Air Traffic Control Centre, you'll find some stuff, but you won't find much because a lot of it was covered by military secrecy requirements. And that will also limit to a certain extent the sort of stuff I can talk about. But it turns out that the air traffic engineering requirements are broadly similar. So there's quite a lot of flow of people between the civil and the military side. These days, in particular, most of the civil the military air traffic engineering people are actually civilians anyway. They're no longer uniformed RAF people. So that fixes that sort of side of things. So how did this all start? Well, first of all, in the closing phase of the war, it became very apparent that we needed some sort of control at airports so that you didn't get two aircraft trying to land on the same runway at the same time. Fundamentally, that was really what it was all about. So tower takeoff, landing, airfield movements, something's taxiing along the runway, it's not a good idea to have somebody also trying to land at the same time. You may or may not be able to see what's going on the ground. So that was really where air traffic control first was developed. During the Second World War, radar was developed, and that allowed us to do what's called approach control as well, which is basically sequencing aircraft coming into land, so they don't arrive at the runway at the same time. They arrive at a suitable separation, a minute or two, or whatever it might be. But this created the next question on, which is, okay, so the radar at the airfield maybe works over 20 or 30 miles range, fairly typical range for airfield radar. What happens to en route traffic, which is between airports? And so the idea of en route control centres was initially coined in the late 50s, early 60s, but it was essentially limited by the technology capabilities. So because we couldn't really move radar data very far, these air traffic control en route centres were placed very close to major airports. Hence West Drayton, which is just north of Heathrow, Manchester, which is at Manchester, actually at the airport, used to be, and Prestwick, which similarly was just at the airport. And this meant that we could capture the radar data they had and use it directly. So what would happen before we had that was that an aircraft would take off, let's say it was taking off from Heathrow and it was going across to the States, to Boston or something like that. What would happen is the aircraft would take off, It would get to the limits of the radar range of the departure airfield. Now it's got nobody to talk to. Well, what it would actually do is it would talk to the next airfield along the way. That made sense, so maybe Luton gave some coverage, or maybe Birmingham, or something like that, depending upon what the routing might be. And that was fine, but the problem with that, of course, is that these controllers aren't there to control en route stuff. They're there to control stuff that's taking off and landing. So this was essentially muddying the mission for these people and requiring different levels of training, different sort of equipment, and so on and so forth. So that's really why the en route control center came along. So en route, only radar, nothing else, nothing to look at all, apart from blips on a radar screen. And we've covered the other points there. Today, just to sort of turn around where these control centres are, Manchester closed a few years ago, back in 2008. London Swanwick, as it's called now, Swanwick, I mean, it's only the Americans who could call Swanwick London, but the Swanwick is the southern, if you like, control centre, and Prestwick remains operational, albeit in a new building for handling the stuff north of the border, north of 55 degrees north. Okay, let's now start getting a bit more into the detail of air traffic control. There's really two aspects of air traffic control, and they're both part of the same problem. One is flight data, which is really the flight plan. This is what the aircraft intends to do. So an aircraft will lodge a flight plan saying, I plan to fly from this airport to that airport via this routing, this particular altitude, and so on and so forth. Effectively, as I say at that bottom bullet point there, what the flight intends doing. It never ends up by doing that. It might do something fairly close to that, but it never ends up exactly doing that. It will always end up with slightly different routing, different altitude, and so on. That information is captured on one of these. These are called flight strips. And the flight strip is effectively a progress indicator as the aircraft moves through a control sector. So believe it or not, on this little strip, which is about 8 inches long and about an inch high, you can get all of the information about what the aircraft's doing, and then you can sequence it through through your space. Radar data, of course, is the opposite. What radar data does is it gives you the current position in real time, and it does have to be in real time. It gives you the actual altitude, or at least it can do. It can also alert you to conflicting traffic. You see two worms on the screen which are getting a bit close to one another. You do something about it rather quickly. And so we can characterize this as being what the flight actually does in real time. And the answer is you actually need both of these. You can't just do one part of it, you need both of them. Let's talk a little bit more about flight data then before we get on to the real nitty-gritty. Two types of traffic. There's the scheduled commercial airlines, and most people will tend to think that's mostly what air traffic control is. It might surprise you that actually commercial air traffic is only about 10% of all air traffic. It's very, very small. It's just the bit everybody knows about because they get into an airplane to go on their happy holes. But actually, it's a relatively small amount of traffic. That's the scheduled, what's called scheduled. Then the other type of flight traffic is unscheduled, which is really everything else. It's military, general aviation, people like me flying around my little airplane, business jets, and so on and so forth. And that's by far the bigger part of it. There's also two types of airspace. There's what's called controlled airspace, which has various different classes in increasing levels of severity. And this little picture here shows the general layout of the controlled airspace across the United Kingdom. And as will come no surprise, the big lumps of it, of course, are around London, out towards Europe, around Manchester and Liverpool, and then the Scottish area, because that's handling stuff going across to the United States, but it's also handling stuff inbound to Scottish airports, London and Glasgow and Edinburgh in particular. Then outside that, there's uncontrolled, or what's called open FIR, Flight Information Region, Class G airspace, the lowest class of all, where essentially you can fly around and not talk to anybody if you want to. Silly, but you can do it. Not many people do. Most people will want to talk to some sort of air traffic control function. But it's perfectly feasible in all those green bits there, and indeed underneath. These things don't mostly go down to the ground. The only place where they go down to the ground is these mauve-coloured or purpley-coloured bits where the controlled airspace goes right the way down to the ground. Most of the rest of the time, the lower level of it is 2,500, 3,000 feet maybe, something like that, maybe even 10,000 feet. A little airplane, you can fly underneath that perfectly happily. So it's a three-dimensional problem, this. You can't represent it on a two-dimensional screen very easily. So flight plans, which we were talking about earlier, are required if you want to enter or transit controlled airspace. In other words, you want to go into this stuff here. But they're optional outside controlled airspace. So the general rule of thumb is if you're doing something like, for example, flying across water, even if you're in uncontrolled airspace, you would lodge a flight plan. because that gives all the information the emergency services need if you disappear off the radar. But otherwise, I mean, if I go for a little flight from my airport, Carlisle, I wouldn't lodge a flight plan. Under any circumstances, there'd be no reason to do so. If you are flying without a flight plan, but you want to enter controlled airspace, which happens all the time, you have what's called a pop-up flight plan, where you can get a flight plan allocated to you by the controller who's responsible for that airspace. So that handles that problem. Yeah, you can see the sort of details there. I won't go through that by word. But effectively, it is essentially the intended activity of the aircraft. And there are thousands of these every day filed in the UK. It's a big, big problem dealing with all of these. All used to be dealt with teletypes if you go back in the day, but that went away quite a long time ago. And of course, you can imagine this was an early candidate for computerization. Radar. Radio detection and ranging was developed in the last stages of World War II, although actually I was doing a bit of research on this, and it turns out the very first concept of radar was first demonstrated in 1922, would you believe? Not for commercial airlines there is, for non-commercial and GA, generally speaking, not. So the idea, really, they don't want to charge for these things because they want to encourage you to do it. So, you know, you don't want to discourage people by saying, oh, that's going to cost you 10 quid. Well, I won't bother in that case then. So you really don't want that situation. And these days it's all done online, of course, as well. You know, you just fill in a form on internet and it gets sent off. And all sorts of things happen then. Right, so there's basically two types of radar, primary and secondary. And we'll talk a bit more about that in detail in a moment, but suffice to say at the moment that secondary radar is what is pretty well exclusively used in the civil world these days. All these radars effectively are analog systems, because what they're doing is they're using the flight time of a radio signal, time to get out to and back from the aircraft, as a means of measuring distance. Straightforward. We know the speed of light, so we can compute how far the aircraft is away. Because the antenna has a very, very narrow beam, we know what angle the antenna is pointing at, so that gives us a position in space. Doesn't give us the altitude yet, but it gives a position in space where that aircraft is. With reasonable accuracy, certainly better accuracy than you need for normal separation. So at 30 miles or so, you might be able to differentiate between two aircraft which are half a mile apart. You'd never get them within half a mile or so of each other normally. That would be far, far too close. But what you're effectively getting is radar video. This is effectively all the returns coming back, which are just like video. And to begin with, they were sent across coaxial cables, which meant you could get around about 3, 4, maybe 5 miles or so before the signal started deteriorating. These days, you do a bit better. But that's why the early air traffic control centres were so close to airports, simply because of that. The analog to digital transition started in the 60s, but for a long time, the modem technology simply wasn't there. In the early 1970s, when I first started coming across this problem, we reckoned we could just about get all the radar returns from one particular radar down a 2400 baud line. We did not have 2400 baud modems. It's hard to think that it could have been like that, but we did not have 2400. We had to wait until the mid-70s before we got that. So that was a fundamental block to progress. So primary radar, really quickly here, simple return echo timing. Sends out a signal, it gets bounced off the metalwork of the aircraft, comes back, we time how long it took. It has lots and lots of issues as a result. It's not just aircraft that reflect signals, ground things do as well, so you get ground clutter. You don't get any altitude information. What you're actually getting is a slant range. If the aircraft's up at 5 miles and he's overhead, the radar will tell you he's 5 miles away. That's not very helpful. No altitude, there's no identification. What we used to do with primary radar is the first thing you'd be asked when you got to the controller was he would say, turn right, heading such and such for aircraft identification. So you then turn right, he sees a little worm on his screen, turn right as well. Oh, that's where he is. Then he gets his China graph pencil and writes on there the call sign of the aircraft. That's how it used to be. And limited range, because the aircraft is not a very good reflector, you have to transmit an enormous amount of power to get a reasonable signal back from 30 or 40 miles away. No use, longer used in civil aviation. Secondary radar, well, that has its origin in wartime information friend or foe. This is a transponder-based system where we send up an interrogation from the ground. The aircraft then responds with various information, including a thing called its squawk code, but it also sends back other information. It can send back what's called mode C, which is altitude information, and it can also send back other information as well, not really related to the ground interrogation, but these days, people who look at Flight Radar 24, for example, what you're looking at is a thing called ADS-B, which is automatic dependent surveillance. It's a broadcast from the aircraft that effectively continually updates its GPS position and altitude and a few other bits and pieces as well. It's become much, much more common since we lost a couple of aircraft over oceans. MH370, for example, has caused this to be developed much, much more rapidly. And in particular, it's caused ADS-B, which used to be directed at the ground, to be directed up to satellites as well these days, so we can see where aircraft are when they're over the ocean. Most people would have difficulty thinking that until this came along, which is really in the last 10 years or so, once an aircraft got outside a range of ground, we had no idea where it was. Simply no idea. All we had was what the pilots on HF radio told us. And most people were this is why you could lose an aircraft like MH370 and never find it again. So ADS-B is an important major addition which has come along really as a result of MH370. And as I say, they had to refit all the aircraft with antennas on the top of the airplane as well, so they can send information out to the satellites. And never underestimate the amount of data we're talking about here. They've had to launch an awful lot of new satellites to handle that amount of traffic. So this has taken a few years. It hasn't happened overnight. The squawk code is allocated to a specific aircraft, maybe at the beginning of the flight, and it might hold that squawk code all the way through, but more usually it will hold the squawk as it's transiting a particular zone of air traffic control. But the thing is, at any one point in time, there is a unique relationship between the squawk code, which is a 4-digit octal code, and the aircraft. So now we have a way of actually specifically identifying the aircraft on the radar.
Only 4 digits?
Yes, only 4 digits, yeah.
So I'm sure in the sky at any one time.
Yes, but we're not interested in the ones which are outside of our zone of control. That code can be reissued 30 or 40 miles later, maybe 50 miles later, something like that.
Also, if it goes from the UK to France,
Well, it might carry the same squawk all the way through. It might not, but whatever it carries, it's only there for the duration of the aircraft's flight, and during that flight, other squawk codes can be allocated around it perfectly happily. As it happens, you've hit on one of the issues with secondary radar, which is one of the reasons why ADS-B has become much more common. ADS-B has a 32, I think it is, bit address, which uniquely identifies every aircraft in the world, and that is sent out on the ADS-B transmission. So ADS-B, eventually, one of these days, ADS-B will replace secondary radar. That's the plan. That's the grand plan, but it's way over the horizon, yes. Probably another 10 or 20 years away, I would think. But they will be thinking about it. So, yeah. Mode S is a form of transponder code. That's so there's in the secondary radar there's various different modes. Mode A gives information on the aircraft call sign. Well, it's code, it's squawk code. Mode C gives altitude information, and Mode S is the secondary information, which can include aircraft call sign and so on. Effectively, it references into this 32-bit code. Yeah. So, as is always the case with these things, you go through stages, and ADS-B uses the same process, but it's going to take a little while before ADS-B takes over the whole thing. So, yeah, but Mode S is actually selective. What Mode S is really there for is to fix the problem we were talking about just now, which is you get too many aircraft, most of whom you're not interested in, so you need to be able to get rid of clutter. Well, Mode S allows you to do that because you can select, hence the S part of selective, you can select which particular subset of aircraft you're interested in at the radar display. So that's really what that's for. Now, this was the first time that computers were ever used. What we've got is 4-digit squawk codes. What we want is the call sign. So very early on, and this is before my time, PDP-8s, a whole load of them, I think there was about 30 or 40 of them because of the sheer volume of traffic, were being used basically just as ginormous lookup tables that you could edit. And effectively what it did was you pushed a 4-digit squawk code, and out came the call sign of the aircraft. That's all it did. Nothing more and nothing else. And it used up a bunch of PDP-8s. It was quite fun. I remember they were still there when I got there in 1973. But they were starting to come to the end of their life by then. Other things were coming along. But that was probably the earliest part of computerization of air traffic control. Now, so with all that in mind, and we'll get onto the computery bits. So we said modem technology delivered 2400, and then fairly quickly after that, we had 9600 baud. That suddenly became enough to get the amount of data that came from a radar head down somewhere else. We could send it anywhere we wanted to in the country. And that really changed everything. They were very expensive, but everything in air traffic control was expensive, so it didn't really that much matter. You should see what we paid for the 9020. But the other thing that was happening was computer power was increasing very, very rapidly. We were starting to be able to talk about large core stores of 128K bytes. My word, this is what it looked like in the IBM mainframe that we got in 1973. That was 128K bytes of core memory. And, of course, larger capacity disk drives. Although, this might surprise you that until something like 1978, the whole of the airspace program was run on tapes. We didn't have any disks in the system at all. Going against that, this was a period of intense growth in air traffic. This was when the 747 became a thing, and the 747 took the cost of a flight across the States from about £2,000 to about £200. This had the inevitable consequence that a lot more people started travelling. And this was a massive, massive growth in air traffic, which we didn't see again until the birth of the low-cost airlines 25 or so years later, which had a similar huge increase in the amount of traffic. So effectively, we were chasing a problem which was continually getting worse, and the question was, could we ever manage to overtake it or not? Well, we did, is the answer, basically. This is where I spent quite a few of my years, at West Drayton, the first en route centre. So this is what it looks like. This is the actual building, no longer there, now a block of houses, I think. This is what a radar control console looks like, and this would control a sector of airspace in the United Kingdom. The sector would be a variable size, depending upon how busy it is, and it would vary between night and day, because there's less flights at night, so you can get away with fewer controllers for a given amount of airspace. But that's what, and this is a more general view of the control room. To give you some idea of the scale, there's another bit behind here, but that's probably, I don't know, 50 metres from one end to the other. It's quite a big room, and I spent many happy hours in there. Well, we had several goes at getting computing into air traffic control. The Marconi Myriad was an amazing machine, and it's still considered as being way ahead of its time, and we had one of those. A three-way arbitration system, effectively three processors working on the same problem, and then an arbitrator which worked out which had got it right, and taking the best of two, effectively, or best of three, best two of three. And it was originally intended to cover civil, military, flight, and radar data processing. In other words, the whole fandangle. In the end, with all the increase in air traffic, by the time we'd actually managed to program it to do all these things, it was actually only used by the military. And it was only really used by the military for flight control. It wasn't used for radar control because they piggybacked on the back of our radar control. So we have a problem. We have a problem that we're continually behind the curve. There's only one thing for it. We have to come up with an audacious plan. And the audacious plan, basically, was to become the 21st American Air Traffic Control Center, because, guess what? They had exactly the same problem, but they got rather more money to throw at it. They also had IBM over there as well. So they had commissioned, this was back in the very early 1970s, they had commissioned 20 en route centers scattered around the United States, which would do that. So we chatted with them and we said, you know what, could we become your 21st? We'll buy exactly the same hardware from you, from IBM, and if we can have your software, we'll have to modify it quite a fair bit. But so that's what we did. So we became the 21st FAA en route center. As an interesting little side note, by the way, there's still 20 centers in the United States. So they got it right, and eventually we did as well by doing this. So that was part one of the audacious plan. That computer alone in 1971 probably was when it was bought, was £10 million. Imagine what that means. And that was just for the hardware. Just imagine what that would cost today. In today's money. Anyway, the thing where they really excelled themselves, and which actually I still find astonishing to this day when I think about it, is that they decided they were going to go and do their own thing on the radar data processing system. And they were going to use Digital Equipment Corporation computers, which at that time was still quite new stuff. So instead of having stuff which typically we would expect to start bringing technology into our systems, into air traffic control, when it had been around for 5 or 10 years. In other words, it was known that it was going to keep on working. Now we were looking at stuff which had only really been around for a year, maybe even a bit less than that. And the reason we did this was because the FAA's approach was to use another big IBM mainframe, the IBM 9020E, and a Raytheon display system, which cost another 10 or 20 million quid, and it would have been just total ridiculous overkill for the UK. But to decide that we would go and roll our own first ever flight radar data processing and display system was, I think, really quite audacious. And we did it. And that's the remarkable thing, we did it. At the time, it was DEC's largest single order in the UK, and it might have remained so for quite a few years. It was something like 60 or 70 DEC machines in one order. And it was developed jointly by Plessey Radar, part of the Plessey organisation, and National Air Traffic Services. I worked for NATS, but I spent a long time down at Plessey at Addlestone, or as we used to call it, Addlebrain, which is where we did all the development work. So, enter the mighty IBM 9020. You don't see computer rooms like this anymore, do you? But this is what we used to deal with. I joined the storyline at this point. This is where I got involved, and that, believe it or not, is me. That is a 23-year-old John Linford doing some kind of a test with these guys who are engineers. By this time, I'd moved into software, so I'm doing some kind of a diagnostic test with them or something like that. So let's see what we've got here. Well, that's two IBM 360-65s in old speak. Round the back here, you can see two IBM 360-50s, which are the input-output control elements, and down the back there, you've got peripheral adapters and so on and so forth. And there's more. You're only seeing about a third of the room here, maybe not even that, actually. A massive, enormous machine. And what was fascinating was there was all this bunch of young people in their early 20s, basically were running riot over this stuff, developing software, doing hardware, fixing things, and so on and so forth. To put that much faith in such young people was just quite remarkable. Another aspect of the audaciousness of this project. Very few of us were over 30. So you can see the kind of numbers we're dealing with there. It was a triplex system, but we could actually run actually the whole thing would run on a simplex. We would never do that, but it could run on a duplex, and it was configurable by software. So basically, you've got all these various different component parts of the computer. You join them together with a dangerous construction called SCON, set configuration, which would basically join together all of these parts of the computer system into a working computer, a computer which had input-output, had disk capability, had memory, and so on. All of these elements were different. You know, storage was in a thing called a storage element, which had to be configured. So your program had to know what it had configured, because the next instruction was probably going to be in a completely different box, which you just configured. It was interesting writing SCON instructions. So, the IBM 9020 was there to do flight data processing and radar data processing. You can read through that. I mean, we've pretty well sort of covered the sort of stuff we were talking about before. But let's focus on the radar data processing for a moment. It processed incoming raw data. This is coming in from the radar heads. And what it did was, if you think about, you've got radars scattered around all over the country. Instead of saying, okay, well, we've got this circle where that radar is providing radar data, what it did was it merged all of those different circles together into a mosaic, which was effectively a whole total coverage of everywhere which had some radar cover, and it just joined all the bits together. So the whole of the UK had a single mosaic radar image, if you like. This was a very interesting project. It causes all sorts of problems. Remember that radar is an analog system, effectively. It's dealing with time, which meant that radar 1 might report this aircraft in that position, and radar 2 reports it in that position. Well, of course, ultimately, you're illuminating multiple radars illuminating the radar. So what you actually end up with is a splodge of possible positions. And so we write some very clever software called collimation software, which basically worked out the position of it from all those splodges. And then what it did, once it started narrowing it down, and from then it would say, okay, I predict it is now going to be, the next time the radar comes round, 4 seconds later, it's going to be in this position. And usually it would be, because usually aircraft sort of tend to fly in straight lines. But if it missed it, if for some reason it didn't fit in there, then it decollimated out until it found it again. And it was continually moving in and out. So we could get the actual position of this aircraft down to about 100 meters, which is astonishing, really, when you think about it, by this process of collimation. So that was quite good fun. Part of that also was collision detection and avoidance, which hitherto had entirely been done by controllers, but now we started writing software to be able to do that. So this was all sitting inside the radar data processing. So far, we haven't found a way of actually getting that out to any users, to the actual air traffic controllers. All we're doing at the moment is basically fiddling around with bits in order to build this really clever radar thing. This was a joint civil-military project, as you can imagine. So now we move on to the DecI bits, the bits you're all interested in. Sorry about the long introduction, but I think most people probably don't really know that much about air traffic control, so I think it was probably useful to go through that. So this is the PDP-11 based bit, wholly developed in the UK by Nats and Plessy, and essentially what that does is it takes the data from the 9020, this mosaic radar, and passes it up into the sector sizes that the controllers are currently operating at, then displays it at that set. That doesn't sound like much job until you look at how much data is being dealt with and the fact you've got something like 40 or 50 controllers scattered around the place in a rather large control room, and we haven't got the telecoms yet to get the data to all those positions in radar terms. So it was quite interesting. So it took this process data from 9020, and effectively we had to get information from the 9020 into a DEC Unibus environment. And we'll get onto that in a moment, but that was an interesting challenge in its own right. In addition to that, we also had a completely independent bypass system. They were scared, and understandably so, that this might not work. So right from the very beginning, they said, we need to be able to bypass all these terribly clever things that sound marvelous, but they've all got to work for the system as a whole to work. So we had a bypass system as well, which effectively bypassed all of that. And it's interesting that this ended up by being a civil-only project, but the reason why I left the CIA and went into industry was because I was actually headhunted by the people who were evaluating the military's next requirement for air traffic control, which is UCAD's, United Kingdom Air Defence Ground Environment, and UCAD was going to use exactly the same systems. So, of course, I had all the knowledge by then, and that's as much as I can say about UCAD, but I did have quite a lot of involvement in that as well. So the first challenge is, how do we get the data to the PDP-11s? Who's heard of a DX-11B? Nobody has heard of a DX-11B. I don't think there's ever more than 2 of them in the UK, and we had them both. So essentially what the DX-11B is, it is a interface between the IBM selector channel. It'll actually work on the multiplexer channel as well, but the IBM selector channel in our case, and the DEC Unibus. And essentially, you've got the 2 buses coming in, FIFOs either side of it, and you write some software in the middle to join them together. I did that for about 2 years. That was rather interesting. All written in assembler, of course, and effectively it became a transaction-based. Each radar paint is effectively a transaction. We sort of invented an early version of what these days we would call X25 to packetize that data and send it across the interface so that it would actually get there and we knew it had got there. And it used what they called tumble tables. I think the term FIFO hadn't been invented in those days. And so DEC called it tumble tables, which effectively were first in, first out buffers running in memory, running in core memory. And this had a bunch of programmable registers which allowed you to manipulate those data streams. And this is where my memory becomes a bit hazy. But there was certainly a PDP-11 of some sort which was embedded in that, probably in 1134, because the computing requirement wasn't all that great. Effectively, we just had to instruct it to send the data rather than actually manage the data itself. It wasn't actually handling the data, it was simply handling the routing of the data. And so that probably ran under RSX11S, I think, maybe. But it was programmed in Macro 11, again, I think. Macro 11 was around by then, certainly. But although I did that programming, I've kind of forgotten. What I do remember is we developed into RSX11M, which, again, was an extremely new thing. This is the thing which is so audacious about this. We were doing stuff with technology which had only really been introduced out in the world like a year earlier. We'd never done that before. It was really quite an extraordinary idea. So now we come on to the actual DEC equipment. So the IOCE, the input-output control element there, that's the last vestige of the IBM mainframe. This is the stuff that sends data out to tapes and disks and also to the DX11B. So that's sending out a stream of data on its selected channel, a whole 128 kbits per second. Wow. But, you know, in its day, that was considered as being quite quick. Bytes, actually, thinking about it. Yes, it was a parallel. In fact, actually, you're right. It was a 36-bit word because of parity as well, and it was a parallel interface. So it would be words. Yeah. Yes. Good catch. Thank you.
Everybody says these IBM
They're wide, yes. They're parallel interface, absolutely. No, that's a good point. Well, good catch, Dave. So, effectively what it does, it receives the 9020, the radar mosaic. It's not quite as simple as that, because if we just sent the entire mosaic, we'd swamp the system. So effectively what you've got is a request delivery mechanism where you set the shape of the sector and it then sends the data associated with that sector. So effectively that it extracts this three-dimensional segment, three-dimensional in the sense it's got X and Y, but it's also got Z, height information as well. And then that routes it to the display equipment group, which we'll come on to in a minute. Now, I think I mentioned this earlier, but I'll just reinforce this because it's a very important point. These sectors are not fixed things. So a sector during the day, 7 o'clock in the morning, of stuff coming into Heathrow Airport will be quite small. It might only be 20 or 30 miles across, because there's an enormous number of aircraft that have been flying across, on the red eyes, and you need to have the ability to control those, and a controller can only handle so many aircraft at a time. The general rule of thumb is no more than 20, but in fact, at busy times, you try and bring that down to more like 10 or 15. Well, you imagine how many aircraft are landing at Heathrow, and then you can just multiply that and come to the number of controllers you need, and each controller needs his own screen. So this means that the sector size is dynamically changing during the course of the day, and during the middle of the night, the whole of the UK might only be 2 sectors, for example. So managing the configuration of that's quite an interesting challenge. So the 9020 sends the sector dimension changes as required, because that's all controlled through the 9020. Oh, sorry, I missed something there. So what I should have said is that the DX11B then throws its data on the Unibus into a thing called the Common Equipment Group, which effectively is the collecting point for the entire display system. So here we've got our DX11B. I've lost the IOC now, we know about that bit. The KEG, what that then does is that sends out the information for a particular radar display. And would you believe, this is hard to imagine in today's world, we use an entire PDP 1134 as nothing more than a vector graphics card. Raster-type displays were nowhere near good enough in those days, so all of the radar screens were all vector drawn, and the PDP 11, this guy's responsibility was just to take whatever it was given, which includes the X and Y information, and just display that, and that's all the PDP 1134s did. And that kept them quite busy, I might add. Now, I've drawn this as if it's a bus, but it really isn't. It's actually, I think it must have been RS422. I was trying to remember. I knew it was a serial interface. It couldn't have been RS232 because of its distance limitations. The traffic had to go around about 200 or 300 yards. 485 didn't exist yet, so I think it must have been 422 that we used. So effectively, it's a bunch of serial lines, because there's something like 40 of these guys out there, one for each controller position. Okay, so we talked about all of that. Now, the other thing that we talked about was the bypass equipment group. And essentially what happened there was the radar head would send its information down a modem. I think these modems were also duplicated as well. You had more than one route, so this wasn't a single point of failure. It then went into a thing called the bypass equipment group, and there's one of these for each radar head. So effectively now we've kept that mapping of the radar head right the way into the depths of our system here. And that was running on PDP 1155, we think. I'm fairly certain it was a 55 because the 84 and so on hadn't come along by then. And that goes onto another serial bus, which drives the same display equipment. So the only common stuff is the DEG, the display equipment group. If that doesn't work, well, we've got lots and lots of other controller positions, so you just move the controller to the next console along. Generally speaking, we didn't attempt to put any resilience or redundancy in here. Now, there was also a redundant BEG as well, and I can't really remember what this did because this came along after I'd left, but I think the redundant BEG was mostly there to monitor all of the other BEGs, because remember, we've got 20 or so of these, and it was there to monitor them, handle changeovers and so on and so forth, and if necessary, take on the role of a failed BEG, but its principal function was monitoring. So if we look at that, take that as a complete system, this is what we built. So over here, we've got the IBM mainframe. The digitized radar comes along a modem into the IOC, then across into the computer to be mashed up into a mosaic. It's then sent across to a pair of DX11Bs, one for each IOCE, into the common equipment group. Then it's sent via RS42 to each of the individual displays. And all of that is DEC equipment. which is quite interesting, really. Quite a fun, and to say, something like about I think there was about 40 of these in the original implementation. Now, if you want to see this, you can go and see it today. Well, not today maybe, but maybe next week. The National Museum of Computing, when West Drayton closed in 2008, they took on the last stages of the PRDS, the Process Radar Display System. And they took a subset of that called IRIS, which is really an investigation system, independence radar information system, yeah. And essentially what you've got here is two PDP-11 84s, by this time 84s existed, which are providing the BEG and the RBEG functionality, and down here PDP-11 34, which is driving one display. We used to have two displays. That's the display that we used, that one there. As it happens, right next to it is a modern display like they have at Swanwick. So if you fancy a trip down to Milton Keynes, this is well worth a visit. You'll find a lot more information. You might even find somebody who knows a bit about it down there, because there are people down there. So have a think about that. It's on the Bletchley Park Estates, but it's independent from Bletchley Park. It's an independent organisation. Unfortunately, if you want to do both Bletchley Park and the Museum Community, you have to pay for both entries. But you don't have to. You can, if you turn up at the Bletchley Park gates and say you're going to the National Museum of Computing, they just let you in. You toddle up and in you go. So. Yeah. Yes, that won't be on the tapes. I'll just say that if you're a member of various clubs and one of them is the Radio Society of Great Britain, then you can get free entry as well. So there's ways of doing that. Okay, so this was pioneering stuff. The idea that we would sit down and we'd learn how to do all of this stuff and go and write it and get it working and so on. So on equipment nobody really knew was just a crazy idea. But we did it, and what's really interesting is it worked so well that today's systems have a direct lineage back to those systems. So despite all the huge risks, what it did was for the first time it actually got air traffic control computing ahead of the curve, and it managed to remain ahead of the curve ever since, which is really quite an important thing. But the thing that really, when I think back on it, this didn't occur to me at the time, of course, when I was in my 20s, but there was huge numbers, 30, 40, 50 of us, all in our 20s, who were basically running this. We were writing the code, we were designing, we were managing teams, we were doing this, that, and the other. We were all very, very young indeed. And so, for a relatively staid organisation like civil aviation, to put that much faith in such young people was, I think, particularly back then when that was far less common. Why was it? Well, the reason why they had to do it, they didn't have any choice, was you had to be willing to go and live in the States for a year, and you had to also be willing to travel anywhere in the country that was needed. And older people with families and this, that, and the other didn't want the disruption, so they turned their noses up at it. So the CAA, or National Air Traffic Services, was more or less forced to come back to these relatively young radio technicians and say, if you can be in the States, this is exactly the conversation I had at the beginning of 1973. If you can be in Oklahoma, USA, in a week's time, then you can go. And that happened to a whole load of young people, and that's what we did, and I think we did them proud. I can say that now. So, there we go. But for me, it was probably the most important and interesting phase of development in my career, because what this actually did was this launched me off into a new thing which I'd never really thought of before, which was telecommunications. How do we move data over distances? Because that's what we've been doing. And so it turned out to be very fundamental for me. So, just in closing, a bit of a timeline here. In 1971, they made the decision to purchase the IBM 9020. 1973, that was when I zoomed across to the States for a year to learn all about the hardware of IBM mainframes. By the time I got back at the beginning of 1974, the 9020 was already installed in London Air Traffic Control Centre at West Drayton, but it wasn't yet operational. It was the hardware was there, but they were still debugging the hardware, and they certainly hadn't started putting any software on it. So I was there right at the very beginning of this. As I say, I spent about 2 years writing diagnostic software to get the thing up and running, and so we could demonstrate that it was actually delivering as required. So a lot of time writing a lot of code in IBM assembler. In 1976, the flight plan processing system went operational, so that's 2 years later. So that, again, was quite remarkable, that we went from having a system which really didn't have much software on it to a system which actually now was running, the flight plan processing system, actually within 2 years was a decent achievement. Radar took us a bit longer. We started, I think I first got involved in the development, process radar development evaluation system. That's what the E stands for, and I got involved with that probably around about the beginning of '76. It took until '84 before it went operational. In 1989, the big IBM mainframe was rehosted onto 4381s, about a quarter the size and about 10 times the power. That's what tends to happen. But interestingly, as far as I can tell, the DEC systems continued to soldier on. Occasionally, some of the, for example, the 1155s were replaced with 1184s, which by now had come along. But the PDP 1134s continued to soldier on right the way through until when West Drayton finally closed in 2008. And that in itself is pretty astonishing when you think about it. So around about, the mid-90s, I guess, it was realized that West Drayton had come to the end of its life. It had been designed for an era where everything was connected together using point-to-point cabling, and there was millions of miles of cabling in ducts, and it would be impossible to recast that into a network-based solution without so much disruption that it simply wasn't worth it. We were also running out of space, but more importantly, the military, the RAF, who owned the base, wanted to sell it. They wanted to get rid of West Drayton. It was only ever an administration centre. There's no airport there or anything like that. They wanted to get rid of it. So really, the writing was on the wall for West Drayton. So they designed the National En Route Centre at Swanwick. That came online in limited extent in 2002, and it finally went fully online, where everything was being done at Swanwick in 2008, when LATSI closed, and we had a grand party up at Milton Keynes for all the people who'd worked on the 9020, or in fact on West Drayton, but it was mostly 9020 people. We were all getting a bit elderly by then, but that was good fun to do that. So this is what Swanwick looks like. It looks a bit more modern, doesn't it? Needless to say, entirely distributed architecture, entirely network-based. Each one of these screens you see here is basically a sector, or can be a sector. It's all configurable. Sectors usually have more than one radar controller on them. Not always, but usually. They'll have a controller who's essentially responsible for aircraft coming into the sector, and another one who's responsible for aircraft exiting the centre. And if things are really busy, they'll have somebody involved in transit. Transit's relatively easy. It's getting people into the sector and getting them back out again that's the complicated bit. And to give you some idea of scale, we're probably halfway down I went there just before it went operational. We're roughly halfway down the room at this point. That far point there is probably 50 metres away, so it's still a pretty big place. Because, of course, air traffic's grown again, so there's even more people trying to do it. And that's the building, just there, down Swanwick near Southampton. We've not talked about Prestwick, but we will do now. The other air traffic control centre is Prestwick. And that too has relatively recently moved into its new home, which you can see still in a bit of a state of construction. A totally different appearance. This is the new air traffic control room at Prestwick, and it's totally different technology, but it does the same job. So now let's just talk about that for a quick minute. Evolution. Prestwick and Swanwick they handle the whole of the UK airspace, but Prestwick also handles stuff which is going out across the Atlantic until it gets halfway, at which point the US takes over. A place called Gander in northern Canada actually takes over. So Oceanic at Prestwick handles HF traffic to aircraft which are going across the Atlantic as well. So although they have less other traffic, because it's not as busy up north as it is down south, they're handling all the en route traffic across the Pacific, so that's quite a big job. They have an identical mission statement, but totally different architectures in the implementation. Any idea why? Why would we do that? Well, you're kind of kicking around the right area. What they were worried about was, there's two things. First of all, these have been developed one after the other, so the technology would have changed anyway. But the other reason we didn't want to have an identical solution is, what if there is some major systemic problem that turns up? We'd really prefer that both control centres don't go down. We'd really like that, because either control centre can do both ends. In extremis. It's hard work, but they... I'm sorry? Yes. Yeah. So that's the reason. But approximately 20-year alternating. So every 20 years, the technology is refreshed at one or the other. It hasn't quite followed 20 years, but you can see the general rule of things there during the course of the last 40 or 50 years. So Swanwick is currently going through its evaluation. I think it might have decided on the technology now. Obviously, I'm well out of it. But the technology will take another good many years, maybe 10 years or so, to be implemented. I imagine they'll implement it at Swanwick, because Swanwick has been built to be capable of handling multiple iterations. And then after that, they'll start on Prestwick again. And so it keeps on, and that's how you upscale the technology as the technology keeps on changing. That's how you bring it in with minimum disruption. Okay, so, yeah, we're more or less there. In conclusion, I keep on coming back to it. This was an audacious project. It was the first time that we really got computers working. It was the first time that processing power got ahead of the curve of developing air traffic control. The fact they continued to 2008 is just astonishing. And I suppose you could argue that the DEC-based PRDS was actually an example of distributed computing, albeit it was linked by RS-422. What is fascinating is many of the concepts which were developed there are still in use to this day. Okay, they've been recast, but some of the software has actually been carried across. And one example of that is some of the testing diagnostics that I wrote. And I was astonished when I was talking to a mate down at the National Museum of Computing a couple of years ago. But he came up to me, he says, I was wandering around some of the diagnostic code the other day, and he said, I came across a couple of lines of code that you'd obviously changed, because it had date, stroke JL, and he said, I thought of you. And that was in, let's say it was in 2020, and that would be code I wrote in probably about 1975. That's astonishing, really. That's it. Any questions?
You said we have control in Manchester.
Yeah.
How did we get the data to Manchester? Because I assume we didn't have an 90-20.
No. When Manchester existed, there was no computerization at all. They had big radar systems at Manchester, and they fed into, so a radar would feed to a few controllers. And as time went on, as modems developed, so they were able to switch to other radars. But essentially, Manchester worked by having a controller tied to a radar rather than having a radar mosaic built, and the controller would take a slice of that mosaic, which is what the 90-20 brought. But Manchester has been closed for a considerable number of years now because it was decided that really we didn't need 3 control centres anymore. The telecommunications had got to the point where we didn't need it anymore. Resilience you want to, yeah. We don't particularly want, well, we always used to worry back in my day about the IRA, but now it might be Putin or something like that, decide, plump, and the entire traffic control's gone. Yeah, that's not a good idea.
And presumably in Glasgow, if it's completely different technology.
It's Prestwick, actually.
Prestwick, so there's no IBM kit.
No, there isn't. Well, there's no IBM kit in Swanwick either. It's distributed. I think it's all Intel based, but I don't know the detail of it because I was even retired before that. I went operational, so I can give you a sort of slice with some knowledge in the 70s, but my knowledge atrophies as we get closer to real time.
I just remember a talk at TNMOC. I'm sure he said they still had IBM kit or IBM emulation.
They do IBM emulation, yes. This is where I said some of the code is still my code. Effectively what they've done is they've emulated the IBM environment in order to ease the development. You've got it working. Nowadays computers are so powerful you can afford the waste in processing power to simply run a IBM 360 emulation environment for it to sit in, virtual machine effectively. Now, I don't know to what extent they still do this, because I know their plan was eventually to move away. Part of the problem is that this kernel of code was written in the 50s. Most of it was written in assembler. Can you find an assembler programmer anymore these days? In particular, can you find an IBM 360 assembler? They're all my age or older. So the problem is maintainability.
IBM still run assembler training courses.
Yeah, but not. Of course, we always used to train our own people anyway. But it's a big training program, and you really want to move away from that if we can. But yeah. Any other quick questions? Yes, sir.
So, relatively recently, there have been delays and problems associated to failure of air traffic control systems.
Yeah.
Fairly. Now, is it because the media has picked up on it and heard about it? So, have any similar situations happened your time before they moved to Swanwick?
Oh yeah, all the time. These are big, complicated systems. There's always something failing. The question is whether enough of it fails to start causing problems. Most of the time, to be honest, the failures were not in the computer systems, or at least not in the air traffic control computer systems. We talked about sectors having to be reconfigured. Well, one of the things you have to reconfigure is the telephone exchange, because these guys are talking to people on the telephone all over the world. So you have to ensure that the telephone calls, which have a specific number for that sector, are routed to whoever's in charge of that sector at that particular time. And there was a big failure at Swanwick early on in its proceedings, where the telephone network broke, basically. They found a nasty big bug in the telephone exchange system, and that was what slowed down the Swanwick going fully operational, actually, because they said, no, we can't have this. But yes, of course, computer systems do fail. They fail for hardware reasons, but we've got resilience on that basis. Occasionally they fail because of software or system design problems, and those are much more intractable. But generally speaking, we work on the principle that by the time we actually get to use it operationally, it's basically been torn to shreds. I mean, we have, certainly we used to, I don't know whether they still do, but we used to actually do line by line, jump by jump instruction tracing through the entire code to make sure it could never go where it was not meant to go. This took a long time. The other thing I might add, I missed it earlier, is the way that we do all these, or certainly did, probably still do, all these developments, is they write a requirement specification, and then you write code to that. So far, so good. But of course, the requirement is always changing. It always does, because needs change, ways we do air traffic control change, and so on. It's a continually changing situation. But the approach they take is they don't sort of say, oh, we'll just go and write the code differently then. They go and change the requirement specification, then say, oh dear, the software no longer does what the requirement specification said. Now we go and change the software. So you've got a rather long-winded but very consistent sort of change management system in place. But yeah, stuff fails. And the more complicated you make it, the more stuff will fail. So part of the reason why we were quite keen on the PDP-11 based solution for radar was it had much more redundancy in terms of the display side of things. The Raytheon side of things had big computers that fed 10 or I think 12 radar screens. Well, that's okay until one of the Raytheons breaks. Now you've lost a whole chunk of your capability. So we would need to have 10 of the PDP-1134s failed for that to happen. Rightio. Oh, go on, real quick then, because I'm.
So would you say it was the civil or the military side which really drove this?
Oh, absolutely civil. Absolutely civil, every single time. The military has always been quite well behind. UCAG took another 10 years. So they were probably 10 years behind the civil side. Because there's money in civil, basically. Civil produces money, military spends it. But no, absolutely, civil is miles ahead. Yeah, absolutely. Go on, Dave, last one.
Well, I was going to say, it's actually not related. Well, there was a little point in there that you talked about that winds back into the development of computing, and that was the fact that you get clutter on radar.
Uh-huh.
And both the early computer memory systems came out of radar development.
Correct.
So Kilburn and Williams, who were in Manchester, were working on trying to read the contents of a screen so that they could compare sequential images and remove the clutter
Yeah.
by only keeping the things that were moving. And the guys
Yeah.
at Cambridge and Alan Turing at the National Physical Laboratory were using mercury delay lines,
Correct,
which
yeah.
were also developed at the same time.
Yeah.
So I presume if you have a delay line whose transit time is the same as the dish going round.
It's not the dish going around, it's the PRF of the radar.
Yeah, but you can compare
Yeah.
sequential.
Effectively, what you do is you send out a pulse roughly every millisecond, typically. So send out a radar pulse every millisecond. The response comes back before the next pulse goes out. The one thing you know about a fixed target is it'll take the same time for that pulse to go out and come back as the next pulse. So what you do is you put the previous pulse, or the response from the previous pulse, into a delay line of 1 PRF, and then you bring the next one, and you effectively exclusive OR that with, effectively you change the phase of one, and it cancels itself out. And it's called moving target indicator, and that was very, very common during the period from about 1950 to 70.
Yeah, I mean, I've looked at the forces, but I thought it was quite fascinating. And I also think that quite a lot of the digital stuff did come out
for
Yeah.
example, you're doing upholstery. So it's a very, it's very high
Oh,
precision.
and they're close. And remember that Maurice Wilkes, he started off as a radar engineer, and he brought that skill and expertise to the development of EDSAC.
Yeah, so we've got Kilburn, William, we've got 3 radar engineers building the first
Yeah.
2 operational computers.
Yeah.
And perhaps that's why they didn't get on with it. It's a
Yeah.
better way to do radar.
Right, let's call a halt now. I'll still be around, so do call me if you get any outstanding questions. But hopefully you found that interesting. A bit of a sort of different side thing, but hopefully you found it interesting.
Can I just ask, this evening, there isn't really a plan for food, but one plan would be that we go back to the Brookside, which is easy. But if we do that, we're best off getting a show of numbers, and then Brooke can phone through and get a reservation if we can. So if you are here and you want to go to Brookside for food, do you want to put your hand up? 8, 9, 10. That's 10, I think.
11, 12, 13.
Oh, 2.
13. 13. 13.
Can you do that for us then?
13.
Does that include me?
Yeah.
Yeah. Okay. See what they can do anyway. Yeah. What sort of time? Someone shout 6 too early. 7 right. 6 is fine. 6 onwards. Upper 6, bro. Right, okay, we'll carry on then if we're okay, guys. You want to sit back down again? Right, let me just get the recording. Sitting down? You can sit down? Yeah, good lads. You all right, Nick? We'll get started.
Good afternoon, everyone. Can you hear me?
Just hold that up to you now.
Can you hear me?
A bit closer.
Can you hear me? I apologise for not having a nice presentation like John did, but I'm risking doing some little demos in the machine over here. There's just about enough space for people to get in and come and have a look what I'm playing with. My name's Steve Gough, and I haven't been to this DecLegacy before. This is my first occasion, but I do know one of the people here, Rob, because he lives locally to me and helped me out with some vaxes. So I've worked in the computer industry since university some long time ago. I've been retired for 10 years, and my PDP-11 experience comes in a little bit probably before John's, where he's saying this was new technology. In fact, in the early 70s, we were doing PDP-11 software in all sorts of industrial and laboratory applications, and we wrote our own executive. We didn't have RSX11M. I'll say, well, what did you run on? We run on our own executive. Yeah, bare metal. And in fact, the only computer in the country that was big enough to compile our executive was UMIST at Manchester. So every time we changed the exec, I had to jump in the car, go to UMIST, give them a paper tape, and they would spit a paper tape out. But after a while, when we got the executive working properly, we didn't have to visit UMIST anymore. So when there was a new disk drive or whatever, we hoped it was as close to the previous disk drive, because we had, in macro assembler code, had to change the interface to accommodate the new bigger disk drives. So for instance, we started off with a really massive disk drive, an RS-64, and the 64 stood for 64K of storage. And when we went on site and changed some application code to write protect the sectors, because the software was well known for trampling all over the areas of the disk that it shouldn't be looking at, we had to write protect a sector, and we did that by lifting the lid off the top of the RS-64, pressing a pin down, which stopped the right arm coming up and being able to write. It enabled the read arm to work, so every time we extended our code, we used to have to protect it on hard drive by visiting the hardware, lifting the top off and pressing a pin down. So that's the closest I got to hardware. So I apologize, my hardware knowledge is very limited, but I was playing with the software. And I'm talking here about something that some of you here may know backwards and probably know in more depth than I do, but I know there's a lot of people who don't really understand how many levels of software there is to make a computer work. So for instance here, this is a web page off the website. I haven't got a presentation, but I've got a little collection of computers which I call www.museumofcomputing.com. It hasn't really launched in earnest yet, but it's something I'm hoping to develop if I get any more time. So on the layers, we'll just have a quick overview. So the purple box there is something a lot of people don't even know exists. And in fact, the microcode is something that in DEC computers evolved. So when they went from PDP-11 to VAX, they had this great idea of having instructions which were much more powerful. So on a PDP-11, you'd read a register and you'd move a byte of data or 16 bits of data from one place to another. And then on VMS and the VAX, they decided, oh, we got 32 bits. Let's do much more powerful instructions. It almost became a high-level language. And in fact, they went so far that in VMS, suddenly Sun came along and said, this is, and IBM, in fact, I believe, did the same thing. Sun came along and said, oh, this is getting a bit silly. Let's put it all back in silicon. No more of these complex macro instructions. We'll just do the simpler things again. And all of a sudden, DEC and IBM were in trouble because, in fact, the microcode direction had gone too far. So I've got a bit of microcode here in this, of all things, PDP-11 hardware book. So if you want to pass that round, you can see the microcode of a PDP-11. So when you do a move instruction in assembler, it actually calls another routine, which is down in the microcode. So that for 1105, that listing there shows you all the microcode. Please don't anyone ask me to explain it, because, to be honest, it's way below my level of familiarity.
I think you could argue that it isn't even software. It's really hardware.
Yeah, it's on the borderline. Okay, so that's microcode. Now, assembler, unlike John, I haven't got a flashy presentation, but I have got a handout here. Now, I'm going to put it to you all upside down, because this software is so valuable, you'll have to sign a non-disclosure agreement before you turn it over and look at it. So this is a massive program for everyone. This is an assembler code. Yeah, if you could, that'd be great. If Mark can pass it round. So this is a really powerful program, which I hope to demonstrate by putting it in on my PyDP-11 here. So anyway, this is where the level macro code, where we wrote our exec, where we did all our applications. And when there was a new system, new system shipped to site, that was this one. Here's another one. Yeah. Right, so we got the blue level now, assembler. So we'll go down and have a look at that. So here's the microcode. Right, this is our programming sheet. So if you have a look here on the left-hand side, that's the address in memory where the code is located. The contents is octal numbers, which represent the actual instruction. So in our PDP-11 Bible code, in fact, every programmer had to have that with them, otherwise they couldn't do anything at all, because they may remember 137 is move or jump, but if they wanted to do a register left or something like that, they'd have to remember the octal number to perform the actual instruction. So this is the assembler instruction. Move 14,000 to R2, test R0, and so on and so on. So what used to happen is the bulk of the exec and the code would be delivered on paper tape, but over the years with the applications, which were both, in my case, laboratory data acquisition systems and industrial control systems, changes needed to be made, bugs were found, and if I was sent off to site to somewhere, say in Switzerland or whatever, the first thing I'd do, I would send teletext out with the microcode change, and it invariably would start with a jump out instruction, because you'd have a bit of code you wanted to add a few lines to, so you'd jump out to somewhere else in memory that was free, and you'd add the bit of code that you wanted. So this is what we called a patch. So if you pass that round, there's a patch that was sent to a customer, and we kept our fingers crossed that someone at the customer's side could actually key that in. Sometimes they keyed it in, and you had to jump in the plane because they didn't key it in properly, and they pressed the start button and all hell let loose. It would do, in those days, what it would do, it would jump to address 0, which we called a halt instruction. So if the customer phoned up and said nothing's happening, he'd say, can you have a look on, what's it got on there? 0, it was address 0. It had executed a halt instruction. Now, invariably, if you got on the plane and went to site, you'd go with a paper tape sometimes and put it in a teletype and read it in, and that would be a bit quicker. But 9 times out of 10, you'd go to site and you'd sit in front of one of these. So I've got here, I don't know if you can gather round, but I'm going to be bold enough to try and put a program in earnest on this PDP-11. So the program that you've got, which is just a counter, which is running now, I'll put it in on the front panel, and we'll hit the start button, and hopefully it'll start counting. Right. So the first thing I'll do is just halt the execution that we've got running at the moment. So halt. Now, what I'll do is, knowing my octal addressing system, I'll put 1,000 and I'll load that address. You can see now I'm going to load into address 1,000 the little blink lights program that you've got in front of you. So luckily I've saved one for myself, so I'll be able to put it in. So we'll put in the first instruction, which is a clear, which is 5,000. Deposit it in on the front panel. Fortunately, it increments for you. So I'm going to be able to just deposit again. And I'll deposit 5,200, which is an increment R0. So this little program is just going to have a counter, which it displays on the front panel, of which causes us to see some blinking lights. So the next instruction is an interesting one. It's what's called a reset. So the only reason we're doing that is to cause the significant delay. Because if we didn't have a delay in there, it would be so fast, no one would be able to see it. So the next instruction is a funny one, break. So that means fail. I'll deposit that one. Now that I've got my program in there, which you can see in front of you, let's see what happens when I hit the run key. Usually in demos, it usually fails for some reason. I've got something wrong, but let's have a look. So I'll load the address, and I'll press the start button. And there we can see an octal number just increasing. So it worked, a miracle. And what I'd like to do is to go on to some other levels of software. So it's a very inefficient way of implementing macro code. It takes an awful lot of instructions just to do something. Can you imagine hello world in macro? It would probably be more than the one sheet you've got in front of you there. So it came along with this newfangled thing called an exec, which DEC supplied, and a newfangled thing called high-level language compilers. So I then came along and could use an operating system. So when the new disk came along, you didn't have to worry about how are we going to get the data off this disk. We've got an operating system from DEC, and lo and behold, most of the time, we could read data off the disk without having to write the code to do it. It was wonderful. So the operating systems, RSX11M, which I used to use, which was multi-user system, RT11, single user, and we only had one RT11 system that we supplied, and that was to the Metropolitan Police, where we had an RT11 basic system, which used to test how much alcohol you got in the blood. So if you drink too much tonight, you might find RT11 just checking up on whether you're over the limit or not. And that system was written in BASIC rather than Fortran 77. So RT11 had a limited use. It was great for a single user calculation like you had to do blood analysis. But 9 times out of 10 for especially industrial systems, a BR611M+. So hence we used by and large RSX11M. Right, so here's I've got one over here if you're interested, or sad enough to be interested in looking at that. So that's an assembler level program which we used to use, and for instance, I know John was telling me that they also did macro assembled code on both IBMs and DEC PDPs. So hence the PDP-11. Now languages, now I don't know if you remember, but I've even seen a VAX over there with a 3.5-inch floppy disk. So we had floppy disks, and I've got a floppy disk which most people would recognize the 5.25. But we've got a lot of 8-inch floppy disks on things like RX01s and RX02s, which sometimes surprise people. And there's something as well that macro code could be, or high-level language code could be programmed in. So when I was at university, we could go to the computer room with our new Fortran program that we'd just spent days working out and writing, and we'd put it in on the computer room, and there'd be a doorway like there is for the canteen over there, and we'd bring the cards up, and we'd leave it with them, and then you kept your fingers crossed, because it would be about a week before you got the printout, and on the printout, it might be failure on card 2, which was rather disappointing, because it'd be another week turnaround before you could actually correct the problem in your high-level code and try and get it to work. Okay, so that is Fortran, and on the Pi here, fortunately, it's quite a nice little device in the sense that I can boot one of 15 different OS systems just by pressing a key. So hopefully, if I remember correctly, I'll hold this and we'll boot RSX11M. So the people with Pis will all know what I'm doing here, but if I switch one on and hit the reset button, hopefully on this VT over here, we'll see some RSX11M leaping into life. Here we go. So RSX11M Plus version 4.6. Here we go. Let's fib a bit. That's when I was. And I'm hoping to look for some high-level code, which I'll choose the lunar landing in Basic 2 and show you the different levels. Now, the high-level languages all produce macro code. So if you ran Basic or Fortran 77, it produced that macro code that we've seen me entering on the keyboard there, and produced a task which is runnable. Oh, I should have said no, anyway. Right, so I apologize to those of you who know this PyDP11 a lot better than I do, but with the RSX11M, each high-level language produced macro code that you then built into a runnable task. So typically, the macro code would reference different libraries, one for Fortran, one for Basic, and so on, which did simple things. So on here, you'll have Hello World in Fortran, Hello World in Basic 2, and I hope to spend some time finding the lunar landing in Basic and run that one. But just to point out for anyone who isn't familiar with the PyDP11, if it's the software you're interested in, it's a great device because it's so quick to flip between different OSs and just boot them. So for instance, if I wanted to play BSD Unix or something like that, I'd look up at the table there and put 1002, I think, on the keyboard, hit the reset button, and we're booting into Unix. And we can play around on that. I've got some real hardware at home in the collection, but I think it would have burst a blood vessel and ripped my back if I'd tried to bring any of that along here and demonstrate it. So I appreciate all those bold people who've brought stuff along, and Matt, who's brought, I don't know how many computers along, really embarrassed. So I'm embarrassed just having a PyDP11 here, but I'm focusing on the software side of DEC. While I play around looking for lunar landing, if there's anybody who's got any questions, because I've run through that really quickly, what I've got here, which may be of interest to people, so I've got some early programming cards, PDP-8, PDP-11. I've got some example macro assembler listings, which might be of interest to people. And also, I've got the microcode, which someone might be able to explain what it's actually doing and saying.
It's magic.
It is magic, isn't it?
Need to be hardware. Need to be hardware man to understand that.
Okay, so bear with me a minute while I... right.
Can you talk and type at the same time?
I'm not female, so I can't multitask.
Very good logic simulator with the 1145 microcode. I've taken the 1145 microcode
I think there's someone in this room who's still using a PDP who can speak up.
Still using PDPs.
S-
The Cubus, the discs, the CPUs, the memory, tape support.
Okay, well, rather than me sitting down typing furiously at the keyboard and everyone getting bored silly, I'll just show an example here of a basic high-level program which is people might recognize as Hello World. I think the best thing to do, if anyone does want to see something like Moonlander or so on, if you give me a bit more time, I'll get them on and show you the 3 stages. Basically, the first stage for any high-level language is to create the code and edit it, which I guess most of the people here will be familiar with. The second stage is to compile it, and to compile it you just produce the macro code. And people were very fussy about what you used to create that compiled code, so when we used to go down to Sizewell and talk about putting a new system in for us, they'll say, what are you going to code it in? And we'd say, well, Fortran 77, what else would we use? And they say, well, get out of the building. That's not secure code. If you don't program in Ada, we don't want to know. And so there was a great, but what they didn't really realize is it all goes to the macro in the end. And the security of the code is at the lower levels in some cases anyway, so by being pernickety about using Ada, I'm sure they were right, and Dave will possibly give us reasons why they did, because it was believed that the Ada language, now the things that we used to say, any language that's got a jump statement is inherently dangerous, because you're likely to jump to the wrong place. So the first thing the security conscious inspector would look at is this language got a jump statement? Right, you're out of the room. So if it's nicely layered, one thing has to call another, and you can't jump right into the middle of something. It's a much safer language. So in many senses, Fortran and Ada and things like that removed the possibility. Now, if you're talking about C and things like that, now you are really being able to mess stuff up. And I was explaining to people before, in the early days of the PDP-11, the core memory was so limited that in fact we implemented a system at Wellcome Research in Kent, which collected data from NMR, I'll get the abbreviation right, nuclear magnetic resonance instruments, collected the data, and then that had to be stored because it came up so quickly. So I reckon it was a lot quicker than the air traffic control radar data. I may be wrong. And what we found was it came in so quickly that we couldn't use any exec like RSX-11. We had to implement a special piece of hardware for the RK05 controller, which used DMA and took it straight from the interface, the Unibus interface, straight onto the RK05. So the instrument ran, and then we used to read the data in at our leisure and execute Fourier transforms on it to tidy it up. And in fact, there's similarity in some ways to the air traffic control system, because there was a lot of noise in the data from the instrument. They weren't brilliant. And so we cleaned it up with Fourier transforms. Now what we soon found, and this is why I'm sorry about the route I'm going around in this story, is what we found was we could only do 3 Fourier transforms. And so the people at Wellcome Research said, oh, we need another Fourier transform with these parameters in. So the only way we could implement it was to self-modify the code. So we had one routine which, before it was called, was modified. And the only reason we did that, and this you could never do this in a high-level language, believe me. So in the macro code, we used to say, right, the 2 constants for this Fourier transform are going to be 32 and 71. So we splatted that on the routine, then called the routine. And then we wanted to do another Fourier transform. And the only reason for doing that was the call memory was so inhibiting. We really struggled just to do what we wanted. So in this day and age, and here of an SD card, it beggars belief that so much memory is at everyone's disposal. And in those days also, there was so much space on disks. I'm probably running out of steam a bit here, but I'm more than happy if anyone would like to explore the high-level languages, lunar landing, some nice Fortran programs with some graphics. It probably makes sense rather than you sitting there behind me looking over my shoulder waiting for half an hour for me to get it to work.
Ask a question?
Yeah, sure, John.
Do you want to go back to the first slide?
Yeah, sure. You're going to spot a spelling mistake.
No, it's an interesting discussion. It might just be a terminological thing. That's the one. Now, if we work our way up the stack there, you correctly identified microcode, which I would say is more like hardware than software, really. The next level up, to my mind, is machine code. Because machine code is the octal numbers that you program in, that you were doing there.
Right.
What the assembler does is another level above that, which then turns those addresses into mnemonics.
Right.
Effectively into, you can call it thread, or you can call it my store of this, or something like that.
Right.
Usually it was limited to 8 characters. But, so I think you kind of need machine code in there between microcode and assembler.
I agree.
Well, machine code is quite different to assembler. Assembler, you don't write noughts and ones. You write move A to B.
Yeah, I've got some assembler examples here.
Conceptually, though, it is one assembler instruction is one machine
Oh,
code.
correct. It's a one-to-one mapping, but they are different things.
The only difference is that in machine code, you would go to address 1042. In assembler, you would go to address named Fred. So that's the difference.
It is. But
that is the crucial.
it's a crucial difference.
Yeah.
Exactly.
When you modify the code, you still jump to address Fred.
Yeah.
When you modify machine code, you're no longer jumping.
You've spotted the reason why when you...
Work it out all again.
Yeah, well, you spotted the reason why the machine code systems were in such a mess, because the work required to put in a larger disk drive interface into the exec, when you had to move the address of every I/O device around in memory, would be horrendous. In fact, you'd have to write the whole thing again in machine code. So invariably what we had to do was, as the device handler grew in size, because we knew we couldn't move the physical addresses around, we'd jump out, add a new bit of code.
And that is machine code.
Yeah, yeah.
That is
So,
machine code. But the way I would argue it is, I can't put Fred in those keys there, but I can put the address in those keys there. So they are two different things.
yeah, yeah. Thanks for pointing it out. As I say, this is just my attempt to explain. And I think the thing that maybe some people here don't realise is that the front panel on your PC was kept even on, you had a picture of 1134, which to me is a quite later machine, but it still had the numbers on the front. Yep. And the reason it had the numbers on the front, if there's anyone foolish enough to try and use machine code on that machine, they'd be able to press buttons. So,
I have a friend who's dyslexic, and he actually prefers machine code because he can't remember assembler mnemonics. When we started on 6809, he could not write assembler at all. He could only write machine code. He can remember the numbers, but he can't remember the mnemonics.
well, I remember the new coders who we used to admire, so the new guys came in from university. And in the same way now as when I see my granddaughter typing a text message in on her iPhone, and I think, bloody hell. You know, she replies to me, zip, and then 10 minutes later she gets my reply, and then zip it straight back, and it probably contains about 25. So what we used to admire was when we had the new guys coming in from university, they could play tunes on the front panel there. They'd be wearing the keys out, and the guys with really good memory could, in fact, remember everything on those cards, so they didn't need them. It's only me, dumbos like me, who needed them. Well, if you look at that program there, it ends with a break instruction. So when I first put it in, the thing I always remembered, because I put it in so often, was 137, which is a jump. So at the end there, I put 2 lines in, 137, 1000. And it didn't work. And I don't know why it didn't work. So maybe I'll work it out one day. So, you know, the one thing that we all remembered was the jump instruction. And we had the patch area, and the key thing was that bit at the end of the address space we were using for putting the program in. Put that address in, then put the code that you need to do the change you want, and Bob's your uncle. Okay, well, I'm running out of steam a little. Is there any other questions? I could run through a few examples of some of the applications that we worked in that were quite interesting, but it's probably better for me to do that at any other time in one-to-one. Home, I've got one piece of the museum up and running nicely, which I call the Windows experience. So we've got a personal computer, which came from IBM before the PC, and then we've got an XT, an AT, a PS1, a PS2, and a ThinkPad, and we've got on those different versions of Windows, including my favorite, Windows 1. And the strange thing is, as they went from Windows 1 to Windows 3 and the other later versions of Windows, the standard of the documentation and the reliability of the software just plummeted like that. If anyone's seen Windows 1, there's not much in it, but it works beautifully, and the documentation is actually exceptional. You know, it's almost as good as Apple, so. Okay, well, I'll finish up there. I apologize if I'm not a polished presenter, but if anyone is interested, I can show them some nice Fortran and some nice BASIC, and who knows, I refuse to show anyone C or C++, because even though I've written loads of code in it, I hate it. And Oh, yeah, yeah. In fact, some people would put it between the microcode and the assembler, I think. Okay, Mark.
Right, thanks very much, Stephen.
Sorry, John. Andy?
But I'm just going to say that what's interesting you didn't really cover is that part of the reason for the development of high-level languages, apart from the fact you could write code more quickly, was that it also forced you to write code in a documentable sort of way. So if you look at things like the evolution of algol and so on, it effectively was self-documenting because it didn't allow you to do bad things. The thing that C did was to break that, and that's the reason I tended to dislike C. It lets you do extremely complicated things in a few dozen characters, then you come back to it 6 months later and think, what was I doing there?
I've forgotten which high-level languages let you do the equivalent to a jump. I know C is one of them.
But it's not just that. It's open squiggly bracket XYZ123 does something like working out the answer to life, the universe, and everything. But you have no idea how.
Yeah. Well,
I think the other trouble is it's a big language, and there are parts of it you can write the same case statement, and you can write the same program in so many different ways. And if somebody uses a different style to you, then the code is totally.
It's very difficult to analyse what's going on.
And I came to look at some code the other day where somebody was using a question mark operator, and I had to go and spend ages thinking about what the heck it was doing, because it wasn't a way I would have ever written code. And it might be efficient, but is it understandable?
Well, I don't know whether I admire or hate the Unix geeks who on Gough on the command line can do about something that takes me 3 minutes with a command program written for a DEC machine in one line of gobbledygook, and it parses a directory, creates a file, calls the program that runs the file, all on one command line. So that's my... If I had a nuclear power station, I wouldn't want anyone running Unix with...
Write once, read never.
Now, I mean, not that I have any problem with C, I use it a lot, but it doesn't force a programming standard on you in the way that algol, for example, did. So in many respects, we've actually regressed by allowing more flexibility. We've actually regressed from some of the original ideas of high-level languages, it seems to me.
Well, I think, I'm not disagreeing, but an argument against that is what I've seen, is that in C++ with object-level programming, it's trying to make C look elegant and Ada-like, because you can make tidy, understandable things objects, and then you can call them and use them. So you get all rid of that complex, geeky stuff and hide it behind objects.
Yes, object orientation certainly helps.
Yeah, I don't know if it's died out now, because I haven't been in the industry for about 10 years.
No, not at all. I mean, I program a lot in Delphi, and that's full of object-orientated stuff. It
Yeah.
is object-orientated.
We're becoming more functional programming again.
Yeah.
With immutable data structures.
Yeah.
So that you can utilise multiple cores safely. That's what's happening now.
Yeah.
I mean, that is the big challenge, isn't it? To write code now that uses multiple cores effectively. For as long as I can remember as a programmer, I only ever wrote code that ran on a single
Thread.
single core, single thread.
Oh, really?
Yes. Well, yeah. I mean, I started on mainframes. And
Yeah, sure. And then you
write my Fortran on forms like this and putting them in the post.
You'd be all right with RT11 then?
Yes.
But now you can't do that. You need to have code that adapts, and I see the issues of that with things like the LT-Sim, which is a spice simulator, which has been adapted to run on multiple cores.
Well, I do keep in touch with the industry indirectly through my son, and much to my surprise, I spoke to him recently, and he said Microsoft are starting to write some decent code and systems for a change. I didn't believe him. I thought they would have tangled themselves up in such a mess with different versions of Windows that it should be dead by now, but evidently, no, they're coming back with a vengeance. That may or may not be, certainly in his application area. Anyway, websites and databases.
Yeah, see, that's true.
Okay, thank
Right,
you.
cheers, Stephen. Right, we've got half an hour, and then I'm hoping that we can do a remote. I can have a remote presentation by Steve Davidson. I've been trying to get him to do a talk for years. So Steve Davidson is ex-DEC development, and then he was one of the system managers that looked after DEC Engineering's development systems. So we need to all try and stay awake. So go and grab those coffees, and we'll resume at 4 o'clock. Thank you very much. Thank you very much, Steve. Oh yeah, I know it's yeah. You don't know the interest of each other.
I'm going to have to stay. I can stay until 5, and then I have to go.
Right.
I think it finishes at 5.
Yes.